Welcome to the third part on the implementation of the simplified DLX. In this part, we want to focus on the control of the DLX. This is a finite state machine, and its job is to interpret the DLX instructions. Now, for every instruction, let us denote it by ij, the DLX control executes a sequence of RTL instructions. The execution of this sequence of RTL instructions constitutes the execution of the DLX instruction ij. So in other words, given a DLX instruction, this is a DLX instruction, the DLX controller interprets it or executes it by executing a sequence of RTL instructions, and once it executes all these RTL instructions, the DLX instruction has been executed. Okay? Now, each of these RTL instructions, which you can think of as a small program which executes this instruction, this DLX instruction, each of these RTL instructions corresponds to a specific state of the control, which, as I said before, is a finite state machine. So in each state, you execute a specific RTL instruction, and the way that the RTL instruction is implemented is through the outputs of the control. So the control sends output signals to the data path and the memory control so that the RTL instruction will be executed. Let's see a high-level view of how one DLX instruction is executed. Okay, so now we're focusing on one DLX instruction. The execution of this instruction will require more than one clock cycle, and it is common to consider the following steps in the execution of the DLX instruction. Okay, not all these steps take place in the execution of every DLX instruction, but it's useful to think of these steps. The first step is the instruction fetch. This step always takes place. Here, what the goal is to copy the next instruction into the instruction register. So the PC stores the address of the next instruction, and all we need to do is read this instruction from the main memory and copy it to the instruction register. So this is the RTL that takes place during the instruction fetch. Instruction decode also always takes place during the execution of a DLX instruction. Here the goal is to decode the instruction that is stored in the instruction register. Decoding means that the control decides what it's going to do next once it has understood what is stored here inside the instruction register. Execution is the next stage. Here we need to execute the instruction. For example, if the instruction is an add instruction, then we need to add the two operands and compute their sum. Memory access. This is a step that takes place in load and store instructions, where we need to access the main memory in order to either read or write a word in the memory. Write back doesn't always take place. Here the goal is to store the result of the instruction, say an add instruction where you computed the sum, so you want to store the sum in the correct register in the GPR. Since the DLX control is a finite state machine, we need to talk about its states, the inputs, the outputs, the state transition function, and the output function, and that will fully describe the DLX control. just to get an idea of how the DLX controller looks like, so let's look at the state diagram of the DLX controller. These are the states like halt, ALUI, decode, fetch, and so on. And what you see here are transitions. So, for example, there's a transition from fetch to fetch when the busy signal is 1, and when the busy signal is 0, there is a transition from fetch to decode. Okay, so this is a description of the state diagram of the finite state machine that implements the DLX controller. We see that there are not too many states. There are less than 20 states. And what we want to now understand is how this state diagram actually interprets DLX instructions. Okay, so let's talk about the states. We have 19 states, and we can list the states according to the stage they belong to. So instruction fetch, we have the fetch state. There's one state that is engaged in that step. That's the fetch state. Instruction decode, we have the decode state. Execute, well, we have many states that deal with the execution stage. They're called ALU, test I, ALUI, and shift. Memory access, we have the states which are called load and store. Write back, we have the states which are called WBR and WBI. These are write back states that corresponds to R-type instructions and correspond to I-type instructions. So we have a different state for the write back stage of an R-type instruction and the write back stage of an I-type instruction. We have additional states, for example, states that deal with branches and jumps. These are the states branch taken, jump register, save PC, and jump and link register. And we have states that deal with load and store. These are the states address computation, copy MDR to C, and copy GPR to MDR. Okay. Finally, we have a state called halt for stopping the execution. So if we go back to the state diagram, then we see that except for this halt state, which is a sync, basically the finite state machine goes through fetch decode, executes, say, the instruction, and then returns back to fetch decode to execute the next instruction. And then it may take another path, transition back to fetch decode in order to execute the next instruction, and so on and so forth. Okay? So we have here like an endless loop which is engaged in executing the instructions. Okay? Let's discuss now the inputs of the finite state machine. It's easier to see this through a diagram. So recall we had this diagram with the controller, the DLX controller. This is the data path. Here we have the memory controller and the main memory. And in red, we have a description of all the inputs and outputs of the DLX controller. So let's go over them quickly. The inputs of the DLX controller, well, it wants to know whether the value which is stored in the A register is 0 or not. That will help the controller in deciding whether a branch is taken or not taken in a branch instruction. The instruction itself is sent from the IR environment to the controller so that the controller knows what is the current instruction. And the busy signal is sent from the memory controller to the controller so that the controller knows whether the memory access has been completed or not. The outputs of the DLX controller are better described again through the diagram. We have clock enable signals that are sent from the controller to all the registers, the MAR, MDR, PC, IR, C, A, and B. We have mux select signals that are sent from the controller to all the multiplexers in our design. Let's see the multiplexers so that we're sure we know what we're talking about. Where is the DLX? Here it is. So you see here that we have several multiplexers in the DLX data path. There's this one, there's this one, there's this one, there's this one, and there's this one. And each of these multiplexers has a select input, and the select input is sent from the DLX controller to the data path so that the multiplexers know which of their inputs should be sent as outputs. Let's go back to the controller. Good. So we have the mux select signals, which are output by the controller and sent to the different multiplexers in the data path. We have the GPR write enable signal, which is sent from the controller to the GPR environment to tell it whether it should perform a write. We have ALU and shifter operations, which are sent to the combinational part of the circuit. The ALU gets 5 bits, which we call them type 4 to 0. The shifter gets 2 bits, the shift that indicates whether shift should take place or not, and another bit which tells it if the shift is to the right or to the left. In addition, there are 2 bits, read and write, which are sent from the controller to the memory controller to tell it whether now we're performing a read or write access to the main memory. And finally, we have the jump link and I-type signals, which are sent from the controller to the IR environment to tell the IR environment whether the current instruction is a jump and link instruction or whether it is an I-type instruction. So now let's summarize what are the outputs of the control. We have these signals. These are 3 bits which control the functionality of the ALU. So these are 3 bits out of the 5 bits of the type bits that are sent to the ALU. So this is part of type 4 to 0. We have clock enabled signals which are sent to the registers. So for example, we have A clock enable, B clock enable, PC clock enable, and so on. We have select signals for the S1 mux, and since it needs to choose among 4 inputs, it needs 2 bits of select, and these 2 bits tell us which of the inputs are selected. We have the S2 select signal, which selects between BIR 0 and 1. And this is actually the immediate, the sign extension of the immediate. We have the select signal for the DINT mux, which tells us whether we want to select the output of the ALU or the shifter. The MDR select, which selects what feeds the MDR, if it's the DINT bus or the DI bus. The address select signal, which selects whether we forward the PC or the contents of the MAR to the output of the address select mux. We also have outputs shift and write, which are sent from the control to the shifter environment, add and test, which are again sent from the control to the ALU, and this is again part of the remaining 2 bits that are missing from the type 4 to 0 bits. the memory read and memory write, which are sent to the memory controller. The GPRWE signal, which tells the GPR whether it should perform a write, and the I-type and J-link signals, which are sent to the IR environment. Recall that we have the notion of register transfer language, which tells us what is the effect that takes place in a clock cycle. So for example, if we look at this instruction fetch, then the goal is to load the instruction register with the contents in the memory of the word whose address is given by the PC, and reading the value that is stored in the MPC from the memory is executed by setting a control signal, which is memory read, to be high. So the controller sends a memory read signal to the memory controller. The memory controller is fed by the PC as an address, and now it knows, oh, I want to read the contents of the memory in this address. Okay, now recall that the memory takes time, which we don't know exactly how long it takes, and it indicates whether it is still working on the memory axis using the busy signal. So as long as the busy signal is 1, this instruction fit has not been completed yet. Okay, so once the result of the read is ready, we know that the IR register is supposed to store it. Okay, so now we send from the memory control, we send the current instruction, right? Instruction that has been fetched. So it's the fetched instruction. Let's rewrite it. We send the fetched instruction, which is M, in the location given by the PC. Now we want to store this in the IR. This is our goal, right? We want to have it in our IR. This means that the IR needs to receive a clock-enabled signal. Okay, so this simple RTL requires a lot of work. Let's understand what it is. You want to make sure that the PC is fed into the address input of the memory controller. We need to make sure that the memory controller gets an MR signal equals 1. We have to wait for the busy signal to go down, and we need to set the clock enable of the instruction register to 1, so that when the busy goes down, we will have here in the IR the fetched instruction. Okay, so for every state in the set of states of the controller of the DLX, we can write what is the RTL instruction that occurs in that state, and we can describe how this RTL instruction is implemented by describing the control outputs that equal 1. All the ones that do not equal 1 equal 0 and do not appear here in this table. By active, we mean control signals that equal 1. Right? So if they equal 0, then they are not active. Well, it's just a way of indicating which of the control signals has a value of 1. So for example, in the fetch, the active control signals are MR and IRCE. All the rest of the control signals will be 0. In DECODE, which is the next state that we transition to when the busy becomes 0, we perform some RTL instructions. Okay, and this is very strange because it seems as if none of these RTL instructions have anything to do with decoding the instruction. So the point is that the contents of the IR are sent to the control as inputs. You do not see this now because we're only describing the outputs. So the contents of the IR are sent to the DLX controller, and in the decode step, based on the value of the IR, the control can decide what will be the next state. So this is not something that you see in the RTL instruction. You see this in the transition function of the DLX. So what are these RTL instructions doing here? Well, it's a funny thing. They're not related to decode, but you want to do them just in case, because they might be useful later when you're trying to execute the instruction. So for example, your default is that the next instruction to be executed, it resides in the address which is 1 plus the current address. So you just increment the PC just in case that nothing else, you won't change the PC, you don't have a branch or a loop or some jump. So you just increment the PC because you can during the decode stage, because during the decode stage the adder is free. Similarly, you read the RS1 and RS2 fields from the instruction register, you send them to the GPR and you tell the GPR, hey, perform this reading and store the values that you have read in the A and B registers. For this purpose, all you need to do is send the clock enable signal to A and B. The GPR, if it doesn't get any other signal, will by default perform a read and copy the contents of the register whose index is RS1 into A and the register whose index is RS2 into B. Okay. How is the PC incremented? Well, the PC is incremented by setting these active control signals. For example, you tell the ALU to perform an add. You send a clock enable to the PC so that it gets a new value, and you set the select signals of S2 to be 1-1 so that the PC is directed to the adder and the constant 1 is also sent to the adder through the other bus. And so you're adding a PC and 1, the output of the PC and the constant 1 are added, and the outcome of this addition, the sum, is sent to the input of the PC, which samples this input and stores it because it gets a clock enable. In the ALU state, you take the contents of A and B and you perform some operation over them and store it in C. So for example, this means that the C must get a clock enable so that it will sample its input and store it. You need to make sure that A and B are sent to the ALU. This is done through the S1 and S2 select signals. And you have to tell the ALU which operation to perform. This is done through these 3 bits that are sent from the control to the ALU. We have a state called the test I state, where the corresponding RTL is to compare A with the immediate constant that appears in the instruction. This is an I-type instruction. And for this purpose, you need to route A and the immediate into the ALU. This is done by setting the select signals of the muxes correspondingly. You have to give a clock enable to C so that it will sample the output of the ALU. You have to tell the ALU that this is a test instruction. You have to tell the IR that this is an I-type instruction. And so that you get the right immediate output, and you have to, and so that, sorry, not because of the immediate, because of the C. In I-type, the I-type tells you where the RD field appears inside the instruction so that you would know what the C address is. What is the index of the what is the index of the destination register. Similarly, we have instructions for the ALU in the I type. This would be addition, where we again send A and the immediate to the ALU and store the result in C. So again, we do the same selection signals. We give a clock enable to C. We tell the ALU to perform an addition, and I type is sent to the IR environment as it is over here. Notice that in here, because in this test I state, because we have some comparison we want to do, the type of comparison depends on these 3 bits that are sent from the controller to the IR, to the ALU, together with the test bit. Good. Shift, again, you want to give a clock enable to C. You want to perform a shift by a certain shift amount, which is either 1 or -1. So then you have to know whether you're doing a shift to the right or not. Here you say, I want to perform a shift. Here you tell the dint mux to select the output of the shifter and send it to C rather than the output of the ALU. In address computation, you simply add the A and the immediate and store it in the MAR. It's very similar to the ALU-I, except that you store the sum in the MAR and not in C. Therefore, you have the same select signals. You tell the ALU to perform addition, and notice that now, instead of a CCE signal, you have the MAR-CE signal, because you want to store the result in the MAR-CE. A load instruction is an RTL. A load state executes an RTL instruction in which you access the memory and address given by the MAR and store the results in the MDR. So if you want to store anything in the MDR, you have to give it a clock enable. You tell the address select signal to select the MAR rather than the PC. You tell the memory controller that you need to perform a read operation, and you tell the MDR mux to select the MDR. Okay. Sorry, to select the input coming from the memory controller to the MDR. In a store state, the execution of the RTL instruction in which the contents of the MDR is copied into the memory, and this is done by setting the address select to 1 so that the MAR is sent to the address of the memory controller, the address input of the memory controller. You tell the memory controller that you want to perform a write. The MAR, of course, is sent as an address to the memory controller. The contents of the MDR are sent as the data to the memory controller, and therefore this write takes place. We have more states with similar ideas taking place there. Notice that whenever we want to store anything in a register, we must give a clock enable signal. Here it is in access to a register in the GPR, so the clock enable is actually a write enable over here. Here you want to store something in the PC, so you give a clock enable to the PC. And all the rest is very similar to the things we have talked about. Notice that in jump and link, there are 2 RTL instructions that are executed concurrently in the same clock cycle. Make sure that you understand how these 2 RTL instructions are executed simultaneously in the data path in one clock cycle. So we go back to the DLX controller state diagram. And now I think things are becoming clearer. We understand that in each state we are executing in RTL, and that our hope is that as we go through a specific path over here, and return to the fetch, we are actually executing a specific instruction in the correct way, so that the sequence of RTL instructions that are executed along this path is in fact executing the DLX instruction that we want to execute. Okay. So now let's talk about the transition function. Okay, so we see the transition function is of course depicted here through the edges with the arrows. We see, for example, that usually you stay in a state for one clock cycle and then you move to the next state. Okay, but there are exceptions where you may be stuck in the same state for several clock cycles. For example, when the busy is 1. So you're trying to access the memory. The memory controller tells you busy is 1, busy is 1, busy is 1. You stay in fetch, you wait until the busy goes to 0, and then you continue to decode, knowing that you have successfully stored the current instruction in the IR, and therefore you can continue into the decode state. Similar things happen in the load and in the store states, because these are again states in which you're trying to access the memory. The halt is just a sync. You never get out of it. You stop the execution of the DLX. So we see that in most cases there's the transition from one state is just to a single state. So the out degree is just 1. There is one big exception, and that would be the decode state, where in decode we could go either back to fetch, if it's, for example, a no operation. We could go to branch, save PC, JR, and so on and so forth, depending on the instruction that we are executing. So the number of possible transitions out of decode is in fact 10. Okay, we see D1, D2, D3, up to D10. These are 10 conditions based on the instruction that is stored in the IR, according to which we perform a transition to one of these 10 states. Now, there are other states that have an out degree, which is not 1, greater than 1, but not as big as the decode. And this is the address computation over here, and the branch over here. So let's start with the branch. You perform in the branch, you have either branch equals 0, branch not equals 0. You perform a comparison with 0, and based on the result of the comparison, you have to decide whether you're branching or not. If you're not branching, then you just go back to the next fetch. You already did the increment in the decode, and therefore you are executing the next instruction in effect. If you want to perform the branch, you go to the state branch taken, and in the state branch taken, you update the PC according to the jump that you want to perform, and then the PC has been updated, and now you fetch the instruction that corresponds to the instruction that you want to execute now. Okay, so that was one exception. The other exception is the address computation. Here we're dealing with load and store instructions. So depending on whether we have a load or a store, we go directly to the load state or to the copy GPR to NDR state in order to perform a store. Okay, so this is the other place that we have out degree of 2. The decision of whether you take a branch or not in the branch state, of course, depends on whether A equals 0, because A will store the result of the comparison, and based on the question of whether the instruction is a branch equals 0 or a branch not equals 0, and the encoding of the instructions is such that in the case of branch equals 0, this bit will be 0, and in the case of branch not equals 0, this bit in the instruction will be 1. Okay, and that's how you decide if the branch is taken or not. We spoke about the fact that there are 2 possible transitions out of the address computation state, and that the decode state has 10 possible transitions. Okay, now let's look at a load word instruction. So the sequence of transitions that you follow if you have a load word instruction is you fetch the load word instruction, you decode it, you notice that this is a memory access, you go to the address computation. Now this is a load word instruction, so from here you continue to the load. You stay in the load as long as the signal is busy. Once the busy signal goes down, you go to copy MDR to C, write back immediate, and that will complete the execution of the instruction, and now you're ready to execute the next instruction. Let's see what happens in each state when we go along this path of states. Okay, so this is the execution of a load word instruction. We transition through this sequence of states and go back to fetch in order to execute the next instruction. Okay, so fetch. What happens in the state fetch? The corresponding RTL is copy the contents of the memory in address PC into the IR. How does this take place? Okay, so the PC is directed through the AD-MUX to the memory controller. This will be the address input of the memory controller. The controller tells the memory that it wants to perform a read. So this would be memory read equals 1. Very good. So now the controller knows that it's supposed to do a read from the address given through here. Busy, 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 busy. Eventually, the correct value is given through here into the IR environment, which receives an IR clock enable signal. And it samples the instruction, which is sent from the memory controller and stored into the IR. So this is the execution of the RTL. IR gets the value of M in the address given by the PC. That happens in the fetch state. The fetch state is very special. We might stay in the fetch state for many, many clock cycles until the busy signal goes down to 0. The next state is the decode state. In the decode state, we execute 3 RTL instructions in parallel. These RTL instructions do not have anything to do with decode. They're executed during decode simply because we have free resources in the data path, and we want to utilize them during this time. Okay, how is that done? So the GPR environment is told to perform a read. This happens because the write enable signal is 0. The 2 addresses that it needs to read, the AADR and the BADR, are sent from the IR environment to the GPR environment. So this is not depicted over here, but of course it occurs. So here you send the address of the A and B. You can think of it as RS1 and RS2. Now, of course, you may say, but what happens if the instruction is not an R-type instruction, it's an I-type instruction? In that case, you're just reading something into B, which is gibberish. It's not of interest, but it doesn't cause any damage. Okay. So now the GPR reads the contents of one register given by this index and another register given by this index, and it stores them in A and B. This is how these 2 RTLs are executed. Finally, we need to increment the PC. How is the PC incremented? We take the value of the PC, take the output of the PC, we direct it through the S1 mux into the ALU, we direct the constant 1 through the S2 mux into the ALU, we tell the ALU mux to perform an add. The output of the ALU, which is the incremented PC, is directed through the dint mux back into the input of the PC, and the PC is given a clock enable signal. And that's how the 3rd RTL instruction is executed during the decode stage. Notice that we could execute all of these RTLs concurrently because they used separate resources. Yeah, the GPR is a dual port RAM, so it can perform 2 reads in 1 clock cycle. This is the first 2 fellows. And the increment of the PC takes place through completely disjoint resources inside our data path. The next step, after we did the decode, is to compute the effective address. The computation of the effective address is taking the contents stored in A and adding it with the immediate constant, which is output by the IR environment. So here we send the immediate from the IR environment to the S2 mux, which directs it as the second operand of the ALU. A is sent through the S1 mux to the first operand of the ALU. The ALU is told to perform an add. The sum is directed through the dint mux to the mal. And the mal, of course, needs to store this result, and therefore it gets a clock enable signal. And that completes the execution of the RTL, which takes place in the address computation state. Notice that this requires a single clock cycle. Now, having computed the address and stored it in the mal, we can perform the load, the reading of the value we're interested in. What is the RTL we want to execute? We want to copy the contents of the memory in the address MAR into the register MDR. So we take the output of the mal, we direct it through the AD mux to the memory controller. This is the address input of the memory controller. We tell the memory controller that we want to perform a read. Okay. Now, busy. Finally, the memory controller sends the content of what it has read. So this would be M in the address given by the mal. And it directs it through the MDR mux into the MDR. And it tells the MDR to sample this thing. So we will get an MDR clock enable signal, so that we store inside the MDR what we need to store because we wanted to perform a load. Okay. This does not complete yet the execution of the load instruction. We need to continue. So now what we want to do is we want to execute the RTL, which says copy the contents of the MDR to the register C. MDR to C. Now you notice that there is no direct path from the MDR to C. So what we will do is we will go through the shifter and send it to C. So of course the C needs to get a clock enable. We need to select the MDR in the S1 mux as an input for the shifter. We tell the shifter that there is no shift. Right? This is easy because all we need to do is set the shift signal to be 0. No shift. Therefore, the shifter implements the identity function. The input equals the output. The dint mux will select the output of the shifter, send it to the C register, which samples the input, and from that point on, the C stores the contents of the MDR. Again, this takes a single clock cycle. Finally, we're ready to complete the execution of the load word instruction. The RTL that we need to complete is to store the contents in C in the destination register. And this takes place by taking the output of C and storing it in the GPR. So the GPR will get a write enable signal to tell it, copy the contents of C into the destination register. How does it know what the destination register is? Well, this destination register is sent from the IR environment. The index of this destination register is sent from the IR environment to the GPR environment. Now notice, why do we need 2 separate states for write back? So we have write back for I types and write back for R types. Why do we need 2 states? Yeah? Why couldn't we unify these 2 steps? And the reason is reason is that the CADR, the RD, resides in different places. In the instruction. That's the reason, right? So the place where the RD resides in these two instructions is not the same in an I type and in an R type. And this RD is going to be the CADR. We don't know which one to send, so we need different states in order to know which one we send. Okay, very good. Let's summarize. We described every module in the data path and specified its input, outputs, and functionality. We described the control of the DLX as a state machine. We glued all these components by describing the RTL instruction that is executed in each step or state. We executed DLX instruction step by step, the load word instruction. We gave the full details of the implementation of the simplified DLX. There's no need to learn this implementation by heart. It is merely a suggestion for an implementation. And please try to understand the underlying principles. The best way to see how the design works is by executing all the instructions step by step. Thank you very much.